Good morning, everyone. My name is Le Yu. Today, I'm going to present our research work, Alchemist, a practical attack investigation technique. This is a joint work from Purdue University, University of Rutgers, Sandia National Laboratories, and SRR International. Cyber attacks are becoming more sophisticated and cause huge damage to both enterprise and personal users. According to the data provided by CSIS, 500 significant cyber attacks are detected in the last 10 years. At 2010, only 20 attacks are detected, and in 2019, this number grows to over 100. According to a survey by RSA, over 17% of cyber analysts fail to recognize cybersecurity events. First, let me introduce attack investigation. Attack investigation contains two parts. The first part is a provenance tracking system. A provenance tracking system maintains a record of events that occur during system execution. For example, audio logs is a record used by Linux system. The audio log contains all the system-level events such as syscall. For example, a Firefox process first connects to a remote server. Later, this process downloads a file into the system. And all the system-level events are captured by the provenance system. The corresponding audio log is shown on the right. The second part is a dependency analysis. We need to parse the provenance data and generate dependence graph. Once an attack symptom is detected, the analyst can perform backward analysis to find out the root cause. We look at the audio log on the left. The first audit entry starts from line 1 to line 4. It shows Firefox process with process ID 2553 connects to a remote IP address. The corresponding graph is shown at the right. Similarly, the second audit entry starts from line 6 to line 8. It shows the same Firefox process writes some data to file main.c. The nodes represent the system objects and subjects, and the edges represent the causal relationships. If the file main.c is identified as a symptom event, we can start from main.c to perform backward analysis. Finally, the IP address is identified as the root cause. In attack investigation, we assume the write event depends on all the read events that happen before it in the same process. Such assumption will introduce a lot of false dependency. For example, the Firefox application opens multiple websites simultaneously. One file is downloaded sometime later. With this assumption, these files depend on all opened websites. There are several reasons for dependency explosion, such as long-running process, asynchronous background behavior. Besides, process-level dependency are too close, and application-level semantics is missing. To solve dependency explosion problem, the concept of execution partitioning are proposed. The basic idea is to partition one process into multiple execution units. Events within one unit are causally related, and events across units are thought to be independent by default. The graph shows that Firefox opens many websites and downloads one file. Without the execution partitioning, there exist many false dependencies. In fact, the file should only depend on one socket. For Firefox, a tab is viewed as an execution unit. Each tab will handle one website. The file depends on the website within the same tab. The state-of-art instrumentation-based execution partitioning is called MPI. In this work, it instruments application by annotating their source code. The instrumented part will expose unit-related information to the provenance system. However, MPI have several limitations. First of all, source code is not always available, and third-party instrumentation are not acceptable in enterprise environments. Also, such instrumentation will cause non-trivial overhead for complex applications. Here, we show the overhead of Alchemist comparing to two instrumentation work, MPI and BIP. We choose 12 popular Linux applications to evaluate both the space overhead and the time overhead. We collect 1-week logs from 8 daily used systems. For space overhead, our system introduced much less overhead for complex applications such as Firefox. For Firefox, our system introduced 7% overhead, while MPI introduced 18% and BIP introduced 14.2% overhead. For time overhead, Alchemist has the lowest overhead for most applications. The state-of-art profile-based execution partitioning is called NoDoze. In this work, it builds an event frequency database which stores the frequency of all the events. Then it calculates an anomaly score for each pass based on frequency database. Based on the anomaly score of each pass, the program's execution is partitioned into normal and abnormal part. NoDoze has several limitations. First of all, it highly depends on the quality of an event frequency database, and it cannot handle false dependency caused by asynchronous behaviors. Some work has explored the usage of application log to perform execution partitioning. The state-of-the-art is called OmegaLog. In this work, it uses application logs to identify program execution paths. It then recovers event handling loops based on all execution paths. OmegaLog has several limitations. First of all, it does not work on complex programs that use asynchronous I/O programming model, and it does not derive high-level semantics from application logs. Alchemist is based on the observation that application log provides high-level semantics, such as execution unit boundary, and AuditLog provides low-level details such as inter-process communication. By fusing application log with AuditLog, we can propagate application semantics to system level. Next, we attribute system events to execution unit to preclude false dependency. To better understand application logs, we perform a study of 13 commonly used Linux applications. We ask ourselves two questions. Question 1, how many applications have built-in logging modular if this modular contains unit information? The second question, besides event handling loops, if there exist other execution models. Among these 13 applications, 29 applications has built-in logging modular. Although the rest 3 shared applications do not have log, they have command history. And 31 applications contains information which can be used to identify unit boundaries. After the analysis of 13 applications, we summarize the 5 different execution models. Each application leverages one or several models. The third class, fourth class, and fifth class contribute to background and asynchronous behaviors, which cannot be handled by previous work. Based on the study, most server applications use class 2, which use event handling loops to receive tasks and fork new process. This is why previous work can handle server applications. However, for most UI applications, such as Firefox and Thunderbird, it leverages class 3, 4, and 5. Based on the study, we propose a universal model which covers all these models. This is the system workflow for Alchemist. The workflow is divided into 3 phases: log normalization, log fusion, and graph construction. Specifically, application log and AuditLog are passed into canonical form. The Datalog engine takes predefined rules, queries, and normalized record to generate target relation. We generate a provenance graph based on the target relations. The first phase is log normalization. Each log event in the application and audit logs are passed into canonical form. It consists 20 fields. For example, Firefox connects to a remote IP. We show its audit log and application log here. A1 denotes audit log after normalization. F1 denotes Firefox log after normalization. They share common fields such as time and PID. Meanwhile, audit log has its own field such as PPID. Firefox has its own field such as unit ID. The second phase is log fusion. We define a number of basic relations. These relations can be obtained directly from normalized log. For example, the Firefox opens multiple tabs connecting to different websites such as CNN, Gmail. The IP address for CNN is IP0. The IP address for Gmail is IP1. We can obtain read Firefox IP0, read Firefox IP1 from audit log. read Firefox IP0 means there is a network connection from Firefox to IP0. Also, we can obtain read network Firefox IP0 tab 0 from Firefox log. Read network Firefox IP0 tab 0 means the connection to IP0 belongs to tab 0. Similarly, when a JavaScript file min.js is downloaded and renamed as fcopy, we can also get some basic relations. We define Datalog inference rules to derive new relations from basic relations. We can derive some new relations which are not visible at the Audit level. For example, in the same case, we can derive tab read tab 0 IP0. From this relation, the IP0 is mapped to tab 0. And with this relation, the IP0 is directly connected to tab 0. Similarly, tab right tab 0 min.js. From this relation, we can link the file min.js directly to tab 0. And with these two relations, tab read and tab write, we can derive dependence relationship within the same tab. Dependence IP0 min.js means output file min.js depends on input IP0. In this way, we can remove false dependence from min.js to IP1. Also, some relations are not visible at the application level. For example, dependence min.js fcopy. Also, some relations are not visible at application level. For example, dependence min.js fcopy means fcopy depends on min.js. By fusion application level relation with Audit level relation, we can finally derive relation dependence IP0 fcopy. It means fcopy depends on IP0. To solve the dependency explosion problem caused by Firefox, we need the following inference rules. In total, we have 135 rules. For more details, please refer to our paper. To evaluate Alchemist, we select 14 popular Linux applications. Besides, to evaluate Alchemist, we select 14 popular Linux applications. Besides, we emulate 10 advanced attacks from DARPA transparent computing program and 4 real-world attacks mentioned in existing works. To evaluate the effectiveness of log fusion for execution partitioning, we craft a complex workload for each application. We emulate if and evaluate if Alchemist can attribute events to correct unit. Observe that Alchemist can achieve 100 accuracy for most of them. However, OmegaLog does not support applications like Firefox because of asynchronous background behavior. We use Alchemist, NoDoze, and OmegaLog to generate a provenance graph for 14 attacks. Alchemist outperforms NoDoze and OmegaLog on most attacks. The average precision of Alchemist is over 19%, and the average recall is nearly 100%. Alchemist is related to many works, including attack investigation and log parsing. Alchemist has some limitations. The first one is the log parsing. We need to write a parser for each application. Some work from log parsing area can be evolved to simplify this process in the future. Another limitation is the completeness of execution models. Although we studied 32 most popular Linux applications, there may exist some execution models not covered. This is a conclusion for our work. If you want to know more details, please refer to our paper. Thank you.